So now we're going to discuss a very special kind of relation, and these are called equivalence relations. Okay, and here's the definition. A relation R from a set to itself is an equivalence relation if it has these three properties. Number one, it is reflexive. Number two, it is symmetric. And number three, it is transitive. Okay, so if it has kind of the trifecta of properties, then we call it an equivalence relation. Okay, now when we have an equivalence relation and two elements A and B are related, so that A is related to B, then we say that A and B are actually equivalent. Okay, and we often write, as long as you know what the relation R is, we can just say A is equivalent to B using like a tilde sign. I'll also use A is equivalent to B using kind of like a triple equal sign. Okay, so those are well, that's the important concept, equivalence relation. Now let's look at some examples of that. Okay, so the first example is pretty easy, equal. Okay, and so why does this work? Well, A is always equal to A, right? So that's first property. Second property, A is equal to B implies that B is equal to A. Yes, that's true. So check. If A is equal to B and B is equal to C, that implies that A is equal to C. Yes, right? So it has all the properties. It's reflexive, it's symmetric, it's transitive. That makes it an equivalence relation. Okay. How about equal mod 2? Okay. So what this means is that A is equivalent to B if A is equal to 2. If A is equal to B modulo 2. Meaning, right? This is just a fancy way of saying that I'll say that A is related to B. What that means is that A and B are both odd, okay? In which case they have the same remainder, modulo 2, namely 1, or A and B are both even, and they have the same remainder, which is 0, okay? That also holds for equal mod K, okay? So mod K, that just means they have the same remainder modulo K, so modulo 5, modulo 7, modulo 8. And in all of those cases, equal modulo that is an equivalence relation. Okay. Now let's have a relation within words. They have to have the same letters, right? So for example, cat and tack have the same letters. Okay, so sure, that's those two are equivalent. It actually does turn out that is an equivalence relation, right? Because if word 1 has the same letters as word 2, then word 2 has the same letters as word 1, symmetric. Word 1 has the same letters as itself, reflexive. If word 1 has the same letters of word 2 has the same letters as word 3, then sure, word 1 and word 3 have the same letters, okay? You can even kind of insist that they have the same quantity of each letter, exactly 2 A's and 3 B's and so on. And it's still a symmetric, equivalence relation. All right. Now, whenever you have an equivalence relation, you can immediately define something called an equivalence class, okay? And this is the symbol that we use for equivalence class. We take an element and we put square brackets around it. If the relation that we're talking about is understood, then we can leave it like that. If not, we just write it down here. Okay. So for example, well, the definition of this is simply all B such that A is related to B. Okay. This is just the definition of an equivalence class. So one thing I want you to know is that equivalence class, right, is always a set. Right. Because it is the set of all things that are equivalent to some element like A. Okay. Now equivalence classes come up all over the place, and they're going to be very important to us. So let's get some intuition with them. Okay. So let's take the relation equal. So what are the equivalence classes of that relation? Right. Well, by definition, A of equal is actually defined as the set of all B such that A is equal to B. Right. Well, that's just A, right? Because it's the only one that's equal to that. So that's okay. We found that one. How about this other one? Equal mod 2, right? So let's try a real concrete example. So what is the well, let's try 4. Okay. So what exactly is the equivalence of 4 mod 2, and that's going to be the set of all b such that 4 is equal to b mod 2, right? And that's actually the set of all b such that the remainder of b divided by 2 is equal to 0, right? Because that's the remainder of 4 divided by 2. And that's just equal to the set of all b such that b is even. Okay, so that is actually equal to this set right here, right? It's minus 4, minus 2, 0, 2, 4. And it's just infinite in both directions. Okay. Similarly to that, the equivalence class of an odd number is actually the set of all odd numbers. So the equivalent class of 1 is minus 5, minus 3. I missed one here. Minus 1, 1, 3, 5, and so on. Okay. Here's a somewhat tongue-in-cheek example. If you look at the people in Scotland, I just went there, I can divide them into equivalence classes just based on what is their clan, right? So everybody in Scotland belongs to some sort of ancestral clan. So I can say, oh, here are the MacTaggarts, and here are the, and so on, right? Maybe, right? You know, there's the, it can be ambiguous, right? You know, well, half of my ancestors are for the MacTaggarts, the other ones are for the MacDuffs. Let's ignore that. So, but still, you know, you could see how that would work, and then you have, you know, Bob is equivalent to Fred if they actually come from the same clan. Okay, let's now define what it means to be a partition. Okay. And a partition is actually a collection of subsets of a set that have these two kind of important properties. First property is that if you take the union of all the sets in the partition, you get back the main set. And the second property is that the intersection of any of those two is empty. So what I like to think of is I think of a big set over here like this, right? So this is my set S. And then I'm going to split up that set into some pieces like so. Okay? So that is a partition, and I have S1, S2, S3, and S4, right? And you see that if I take S1 union S2 union S3 union S4, right, I get back S, right? So that's first property, okay? And the second property, if I take, for example, S1 intersect S2, I get empty, right? So so that's the second property here, and that has to be true for any pair. So I have to check all the other pairs, but you can see from the picture that that's exactly what's going to happen, right? So here is actually my mental model of a partition, right? Whenever I think of a partition, that's what I think of. I think of some set being split in those ways. Now let's look at some examples of partitions. Here is a partition of the natural numbers, right? So if I look at the natural numbers 0, 1, 2, and I just define these sets, well, if I take the union of 0, union 1, union 2, oops, that was a great, union 3, union dot dot dot, well, that's definitely going to be equal to that 0, 1, 2, 3, and that is the set of natural numbers, okay? So first property, check. Likewise, if I take, say, 3, and I intersect it with one of the other ones, like 7, then I'm going to get the empty set, right? So that's the second property. This is a partition. Okay. What other examples can we do? Well, let's look at the integers again, right? And as I look at the integers, then I'm going to split them into the set of even integers and the set of odd integers. And you see that if I take the intersection of these, I'm going to get the empty set, because you can't be both even and odd. If I take the union of that, then I get all the integers, right? Because any given integer is either odd or even. So I'm going to end up with all. So this is a partition. The same is also, of course, going to be true of mod 3 or mod 4. If I say the integers mod 4, I have a partition. All the ones that have remainder 0 with respect to 4, all the ones that have remainder 1, remainder 2, remainder 3. If I take the intersection of any of those, I get an empty set. If I take the union of those, I'm going to get the entire set of integers, okay? And back to the Scottish folks, if I simply think of each clan as being a partition, if I intersect two clans, I get nothing, right? If I take the union of all the clans, then I get all of Scotland. That's that might be true, okay? Now this is the theorem that we're leading to, okay? And that is that there's a very close connection between equivalence classes and partitions, and I think you can see it, right? I mean, all the examples were the same examples, right? So so what we have is this. let's say that we start with an equivalence relation, okay? Then I can define a partition simply by looking at the equivalence classes, okay? So if I take the equivalence classes, they create a partition. So why is that? Okay, the first thing that we're going to do is just look at what are the equivalence classes, right? So here they are. I look at all of the elements in S, and I simply find the equivalence class for each element, right? Now it could be that I end up with a set that is just as big as S, the case, for example, for equal. Or it could be that I end up with a set that has very few elements, like when my equivalence relation is odd or even, okay? So keep that in mind, all right? Now, it is obviously the case that A belongs to the equivalence class of A, right? That's just simply because I have an equivalence relation, so A is related to itself. That's the reflexive property, okay? And what that means is that when I take the union of all the equivalence classes, I'm actually getting each element is going to be included in the union because each element belongs to its equivalence class. So if I take the union over all equivalence classes, I'm going to get S, okay? So this is like property 1, right? Now what about property 2? Property 2 says that if I take two equivalence classes, then their intersection should be empty, okay? So let's see. I'm going to take two, A and B, and let's say that A is related to B, right? So I have that they actually belong to the same equivalence class, right? That is, if A is related to B, then the equivalence class of A is the same as the equivalence class of B, okay? Now suppose that A is not related to B, okay? Well, I claim that in that case, the intersection of those actually is the empty set, right? Because otherwise, let's say that C belongs to the equivalence class of A, and C belongs to the equivalent class of B, right? Then what we have is that A is related to C, and B is related to C, right? Which means that A is related to C, and C is related to B because of symmetry. And then this means, right? This would imply that A is related to B, right? Because of transitivity. And since A is related to B, that implies that the equivalence class of A is the same as the equivalence class of B, okay? So that means that if A is in fact not related to B, right, then the intersection has to be empty, okay? All right, so yeah, the equivalence classes actually form a partition. They satisfy both properties. How about the other way around? Suppose that I have a partition, right? Can I define an equivalence relation? And actually the answer is yes, right? And my equivalence relation is very natural, right? We define the relation by saying A is related to B if and only if they have the same subset in the partition, okay? So let's see, right? I want to check that A is related to A. Well, that's easy because A is always in the equivalence class of A, right? There's some partition of S. That means that one of the elements must contain A, and there it is. That's we're done with that. Okay. Now, how about A related to B? Well, in that case, A is equal to, rather, the equivalence class of A is the same as the equivalence class of B, right? So what does that tell us? That tells us that B is also related to A, right? Because two elements are related if they're in the same equivalence class. So we have reflexivity, we have symmetry. Okay. How about transitivity? A is related to B and B is related to C. Well, that means that the equivalence class of A is the same as the equivalence class of B because A is related to B, right? Likewise, the equivalence class of B is the same as the equivalence class of C because B is related to C. Well, if I have two things that are equal, right? Two other things that are and another one that's equal to the second one, then sure, it's transitivity of equality. A is equal to C. And what that means is that A is related to C because we said A is related to C if they're in the same equivalence class. So we got all three properties, right? That means that R is an equivalence relation. So equivalence relation and partitions are kind of two sides of the same coin. If you have one, you can always define the other.